Welcome. In this lecture, let us know the properties of Schrodinger wave equation and its solutions. So the first property is we know that Schrodinger wave equation IH cross dou psi by dou t is equal to minus h square by 2m dou squares. Let's just take for um, one dimension. So only to understand. So the first property is that we can see here that Schrodinger wave equation is a first order differential equation in time because the order of dou psi by dou t is 1. So when that is the case, the thing with this is if we know psi of x comma t naught at some initial time t naught. Now we can determine psi of x comma t um, for all future times, that is for the evolution of this quantum we can determine psi of x comma t for the evolution of quantum mechanical system. So that's the first property, and second property is based on superposition. So it is based on superposition. In this case, if psi 1 and psi 2 are two solutions. So if psi 1 comma psi 2 are solutions of Schrodinger equation, then um, a psi like a1 psi 1 plus a2 psi 2, where a1 comma a2 are belongs to complex number set. So this is also a solution of the Schrodinger equation. So this comes from linearity, that is superposition. So how this superposition is different from the superposition of uh, classical mechanics. So how means in quantum mechanical superposition it reflects the uh, so quantum mechanical superposition it reflects wave particle duality, that is wave like properties of microparticles. So how it is different from classical mechanics is, in classical mechanics if two things are superposed, then we get something in between. For example, classically, let's say that some p1 comma p2 are superposed, then we get in between we get p, so which lies between p1 and p2. But in quantum mechanics, when we superimpose psi equal to a1 psi 1 plus a2 psi 2, then we get psi is equal to psi 1 or psi 2 for a measurement, or psi is equal to psi 2 with respective probabilities, and not something in between psi 1 and psi 2. So this is a peculiarity in quantum mechanical superposition. So the process of measurement that is performed to calculate psi, it will introduce a sudden transition of the particle from the state superposition state psi to one of the states psi 1 or psi 2. So the validity of the superposition principle enormously helps in solving various quantum mechanical um, problems. Next, let us see the third property, which is equivalence of wave functions. Suppose if psi 1 of x comma t equal to some complex constant alpha times psi 2 of x x comma t. This is x comma t. Now the physical observables, they remain unchanged regardless of which wave function is used, either this psi 1 or psi 2. Now let us see how to get so when we how to get psi of x comma t when we know psi of x comma t naught at some initial time t naught. So how to calculate this psi of x comma t? Now to find psi of x comma t, we have to solve the time independent Schrodinger wave equation. This is the case where potentials are independent of time. So we can write psi of, so initially at psi of x, um, this is not t naught, rather it is 0 at some. So t naught is basically time t equal to 0 as the reference. Hence it is appropriate to take t0, that is at time t naught equal to 0. So we can write psi of x comma 0 equal to n equal to 1 to infinity cn psi n of x. That is by choosing appropriate complex choosing appropriate constant cn, we can get this psi of x comma 0 by putting psi n as only the function of x. Um, so to construct psi of x comma t, we have to tack onto each term its characteristic time dependent, that is e power minus I en by h cross time t. So when we solve the Schrodinger time independent Schrodinger equation, we get infinite solutions, infinite set of solutions psi n of x. We get this after solving time independent Schrodinger equation. We get this psi n of x. So basically, it is an infinite set of solutions, and for each psi of n of x, we have a associated energy. So psi n of x has associated energy. For example, psi 1 of x E1, similarly psi 2 of x E2, and so on. And so on, we can take up to psi n of En. So the time dependable characteristic is e power minus En by h cross times t. Now, when we tack on to the term, we get psi of x comma t equal to, let me use another color, sigma n equal to 1 to infinity cn psi n of x e power minus I En by h cross times t. So this is how we get psi of x comma t, that is evolution of wave function for t greater than 0 in terms of solutions to the Schrodinger equation and time dependent uh, characteristics. So here we know that if potential is independent of time, then all probabilities and expectations are also independent of time. However, this property is not shared by general solution explicitly. So exponentials do not cancel when psi square is constructed in that case. So, for example, let us take a general solution with only two uh, set of solutions, so psi 1 and psi 2. Suppose psi of x comma 0 equal to c1 psi 1 of x plus c2 psi 2 of x. Now we can calculate compute psi of x comma t as with its time dependent characteristic minus e1 h cross t. Now when we calculate probability density, this will be equal to c1 square. We get this when we do this. So here we can see that probability is oscillating because it is function of e2 minus e1 by h cross is a constant times t. So it is varying with respect to time. Uh, so basically it is oscillating at angular frequency e2 minus e1 by h cross, angular frequency, we may something like omega a. So this probability density function is oscillating. So this is not a stationary state. So why it is not stationary state? Because the probability density function is varying with time here when we do this linear combination. Hence, the general solution, which is a sum of these two. It is not. Let me write here. It is not stationary state. Mm, yeah. So this is not a stationary state, rather it is a linear combination of stationary states with different energies. So as a sum, this is not a stationary state, but individually psi1 of x and psi2 of x are individually stationary states. So we have done with the property number 4. Now let's go to property 5. It's probability interpretation. Okay, consider a collection of n number of particles. Consider a collection of n number of particles. So basically, consider this as it's large number. Also, uh, non-interacting particles. Take a value d tau. So this is a volume, small infinitesimal volume. So consider these a number of particles are present in this small volume d tau. Now consider their state as psi of r comma t. Now what is the probability of finding the particle in the volume d tau? D tau where d tau um, is centered around r bar. It is centered around. So we have to calculate that probability. That probability will be psi conjugate times psi times d tau. Now average number of particles in d tau. So for every time we use average, we use this notation in statistics. So this corresponds to average number of particles in d tau. that will be is equal to n times the probability. So here this is probability and this is total number. That gives us the average number of particles in d term. Now how we can calculate the probability density function distribution function at any time t. We can calculate. Um, so this is the case of time dependent case where potential is dependent on time. So that's why the probability density varies with time. And so we have time dependent Schrodinger equation here, which will allow us to determine the time evolution of the wave function psi. Yeah. So calculating calculating n for large number of points in space, we can construct probability density distribution function. So every time when I write PB, that implies probability density distribution function for t greater than 0. In quantum mechanics, this implies future times. So this is a great interpretation of probability regarding the Schrodinger equation. Now let's look at the other property. So Schrodinger equation, it is analogous to classical mechanics in this manner. Uh, so in quantum mechanics, if we know psi of x comma 0, then we can determine psi of x comma t, like we have seen in one of the properties discussed earlier. Same like in classical mechanics, it's about it's about determining x of t. So how we are going to determine x of t based on Newton's second law. So Schrodinger wave equation here helps us to construct psi of x comma t. Hence, it is analogous to Newton's second law in classical mechanics. Not in a very serious sense, analogous, just a way of um, requirement or way of approach, I would say. So in the Schrodinger equation, we have seen energy, that separation constant for time independent case. We have seen that as energy. So the seventh property is real quantity. So let's prove this one. So E is an eigenvalue, and it is known that the property of Hermitian is that their eigenvalues are always real. So E has to be uh, E is an eigenvalue of Hamiltonian H cap, hence it is always real. So let's prove why that is the case. You know that Hamiltonian psi is equal to E psi, which is equal to let's assuming that E or plus, suppose if it is complex, we can write in this form times psi. Now this would lead to for the Schrodinger equation, the solutions that what solutions we can expect in this case. In this case, we get um, exponentially growing term in the solution. So what is the solution? The solution is psi. Basically, in eigenfunction, the exponentially growing term in psi. But whenever there is exponential growing term psi in psi, then that will lead to infinity, and it will be non-normalizable. So this it contradicts with the requirement of probability to be finite. Hence, it is not a physically realizable system. So that's why this condition is not true. So E is always real. Let's see the next property. So consider a time independent potential. So where we have a time independent wave function. We know that time independent wave function can be written as so you may use whichever notation, that doesn't matter, but basically understand the concept here. So we may write it as psi of x, or you may write it as f of x, whatever you like, times another function f of t. So yeah, okay. So let's prove that this psi of x can be real. In fact, what I would like to do is I'm considering this psi of x comma t, which is the a solution of Schrodinger equation. Solution of time independent Schrodinger equation. So the thing is, we have to prove psi can be real. Psi can be real function. So psi can be real function. That doesn't mean that psi should not be complex. Psi can also be complex function, and psi can also be real function. In this case, we will prove that. So if we take h cap psi is equal to e psi. Now we do conjugate. We know that Hamiltonian h cap is an Hermitian operator, so its conjugate will be h cap only. And when we do conjugate first, and e is a real quantity, so conjugate will remain same. And we will get now here. Uh, Initially, we have seen psi is a solution to time independent Schrodinger equation. Now, after conjugating, also we get this equation. So here psi conjugate also satisfies the equation. Hence, psi conjugate is also a solution. Now, based on superposition, we have seen the case of um, a solution being linear combination of two solutions. So psi conjugate and psi are two solutions. So a solution like suppose what is the real part of this psi r, that is psi plus psi conjugate by 2. So it is a linear combination with constants 1 by 2. Hence psi r can also be a solution. Can also be a solution. Similarly, imaginary component. Always remember that imaginary part is also real. When we divide with 2i, we will get a real value, and this is also can be a solution. Hence, for time independent Schrodinger equation, psi can be real function because suppose even if psi and psi conjugate or not, um, suppose psi comma psi conjugate are not real or complex, even then both psi and psi conjugate satisfies these equations. Um, and when we do linear combination, we get real quantities. Hence, a real solution, a real wave function also can be a solution of Schrodinger wave equation. Now, ninth property, symmetry and parity. So, in this case, consider a potential v of x which is even. That is a even function. Means it will be symmetrical um, about x equal to 0. So v of minus x will be equal to v of x in this case. Now let's put in the Schrodinger equation. Like it's not, I'm just calculating for psi of minus x, that will give us e of psi of minus x, because both are not, e and h cap are not depending on that x. So this implies that psi of minus x is also a solution. Sorry. psi of minus x is also a solution. Okay. So let me draw a line here to separate. So h cap of psi of x is equal to e psi of x. Now in both cases, this h cap and this h cap both are same because um, the Hamiltonian doesn't change for um, under parity. So when this is the case, so when this is the case, that is potential is even function, then Hamiltonian h cap won't change for parity transformation. So parity transformation is nothing but plus x and minus x. So here we have plus x and here minus x. So under this parity transformation, the Hamiltonian h cap don't change. That's why this equation becomes valid. Yeah. So psi of minus x is also a solution. Now we have psi of x and psi of minus x as two solutions for the time independent Schrodinger equation. And remember that it is time independent Schrodinger equation, that's why v is only function of x. Now let's do linear combination. So if we do linear combination like this, psi of x plus psi of minus x by 2, this will give us an even function. So basically it yields a even function, and as it is a linear combination, this is also a solution. And what can we expect another solution? Suppose if we do psi of x, sorry, psi of x minus psi of minus x by 2, this will give us odd function, and it is also can be a solution. So when the potential is an even function, the solutions can be an even function, or the solutions can be an odd function. So these are the ways of how we understand the properties of each and everything of Schrodinger wave equation, whether it's Hamiltonian or energy or the wave function or the potential. Uh, let's see the last property. So this is giving the energy bound for E, that is bound of the, which is based, which is determined by the potential. Basically it's giving some limit for the total energy E, that is E should be um, greater than V minimum. This is a potential. So in classical mechanics we know that total energy should be at least uh, greater than the minimum potential energy. or it should be equal to V minimum, or it should be greater. So this is the limit basically we have. So we can uh, prove this by solving the Schrodinger equation. I'm just writing a simplified Schrodinger equation like this. This is for time independent case. So if E less than V minimum will be negative. Now when you solve this differential equation, what we get the what the solution we get, it is second order. So we get exponential term c1 e power k x plus c2 e power minus kx. Why only k? Because the roots are same roots, but a plus and minus. The magnitude of the roots is same, but plus and minus. So now what is k? Okay, let's write k as well. So from the equation you can see that k is nothing but k is equal to under root, basically roots of the differential equation, we 2m by h cut square. Let's put v minimum minus e, because we are comparing with v minimum. So what happens when e is less than v minimum? So when e is less than v minimum, we get um, the roots are real roots. And when that is the case, when we have a real root here, and this will be exponential. And when this is exponential, psi cannot be can't be normalized. And this is a physically not realizable system because the psi cannot be realized. Hence, uh, this is not possible. So e is always greater than v minimum. So these are the 10 properties of Schrodinger equation. Yeah, thank you so much for watching. Hope this video helped to understand the Schrodinger equation properties. And please do subscribe to get more videos related to physics and mathematics.